And we are now live.
Welcome to your Daily Dopamine with Dr. Joe McCullough, where we deliver daily doses of education, entertainment, and inspiration. So sit back, relax, and get ready to be dopamine, dopamine, dopamine.
Oh, yeah. All right, welcome to this week's episode of Ask a Physicist Anything. And to introduce today's topic, I'm going to let George Costanza tell us what we're going to be talking about. Come on, George.
George.
Plus, absolute zero.
Whoops. All right, welcome. So my name is Joe. I'm the physics program chair here at Cabrillo College in Santa Cruz, California. Oh, will you stop that? Yeah. And today, Paul is going to talk about absolute zero and beyond. So stay tuned and get ready to be enlightened. Paul, take it away.
All right, awesome. Good to see everybody. So we were kind of brainstorming in one of Joe's classes this morning with the students on what should we talk about at the session today. And one thing that we came up with was a bunch of topics related to low temperature physics. They asked about Bose-Einstein condensates, about those weird experiments that you hear about recently where they can slow the speed of light down to a few meters per second, or according to some reading I was doing in between there, actually stop light cold in its tracks. And in general, the interplay between entropy and energy. In fact, one thing that people asked about was, hey, I've heard that there are ways to get a substance below 0 degrees Kelvin, below absolute zero, colder than absolute zero. And the answer is kind of yes, kind of no there. You can give a substance a negative temperature, and it can be done experimentally. Whether that really means colder than absolute zero, or whether we should define negative temperatures as actually the hottest substances there are, well, I'll come back to that in a moment. My argument would be, yeah, you can get temperatures which are negative numbers, but that is not an extremely cold system. That's actually an extremely hot system. All right.
No way, Paul.
Yeah. Okay. So what happens in general as you cool things off? Why is there such a field as low temperature physics, and why is it such a thriving field? Ever since the 1930s, we've known that cooling off a substance, cooling it to the lowest temperatures that you can manage with the technology of the time, is the best way to study the quantum properties of ordinary matter. So, for example, some of the first experiments that they were able to do in the 30s with these low temperatures were saying if you can get within a degree or two of absolute zero. Now, right now, room temperature in this room is about 300 Kelvin. 300 degrees Kelvin, I always say, but I know for some reason you're not supposed to say degrees Kelvin. You're just supposed to say 300 Kelvin. So, 300 Kelvin in this room. A degree Kelvin is about, there we go. Yeah, damn it, it's a degree Kelvin. Why wouldn't it be? A degree Kelvin is about the same, is the same size as a degree Celsius. So if you drop your temperature by 10 degrees Celsius, you've dropped it by 10 degrees Kelvin, and you're now at 290 Kelvin. Well, absolute zero is at about negative 273 Celsius. And that would be zero on the Kelvin scale. So 0 Kelvin is about the same thing as negative 273 degrees Celsius.
And for those of us stuck using British units?
Negative 400 and something Fahrenheit, I guess.
Negative 461.
461. Negative 461 Fahrenheit, as I was going to say.
Plus or minus something.
Okay. But, hell, I'll even put that up there if we must. So for barbarians among us, negative 461 degrees Fahrenheit.
Yeah,
I hate to say it, but
like
I grew up on the imperial units too, and I long for the day when somebody tells me, picture an object moving 70 miles an hour. And I say, 70 miles an hour, I don't know what that is. I need to convert it to meters per second. But for now, it's still kind of the other way around. You say, picture an object going 30 meters per second, and I have to stop and think, oh man, that's about 70 miles an hour. That's pretty fast. So yeah, Fahrenheit and Celsius, same way. I do think in Fahrenheit, even though I wish I didn't.
Negative 460.
Negative 460, well that changes everything.
It does.
All right. So how are you going to, why do you want to get something this cold? Because you see quantum effects kick in. When you get down to 1 or 2 degrees Kelvin, then, for example, helium goes superfluid. What do I mean by superfluid? Well, all of the helium atoms kind of enter the same quantum state, which means viscosity. The fact that fluids are kind of thick and goopy, and when you stir them, you feel resistance to it. The whole reason why there's such a thing as viscosity is because every atom in, say, a cup of coffee or something like that is bouncing around in a random direction compared to the others. And if I try to stir the coffee and I try to kind of set one layer of it moving this way and the adjacent layers moving the other way, the coffee's going to fight back because atoms are leaking back and forth between the layers and transferring momentum back and forth, and pretty soon it's all going to come to rest in just kind of a big muddle. I'll have added some random motion, some thermal energy to it. I'll have added some entropy to it because the atoms are now moving a lot more randomly than before, but I won't be able to keep that beautiful shearing effect of the 2 layers moving differently from each other. If that cup of coffee were a cup of helium and it were, below about 2 Kelvin, then actually I could. There would be no viscosity. I could keep those 2 layers moving separately because the atoms in them aren't each doing their own thing and leaking over to the adjacent layers. The atoms are all behaving kind of in lockstep with each other. They're all in the same quantum state. So it's a very different phase of matter. Very similarly, if we were going to talk about superconductors, the first superconductors that they experimented with in the 1930s and 40s, you had to again cool them down to just a few degrees Kelvin. This was way before those high TC superconductors that came on the scene in the 1980s, that we still do not freaking understand how they work to this day. But the low temperature superconductors are a little bit better understood. And again, that's kind of the same thing. If superfluids move with 0 physical friction, superconductors, you can send electrical currents through them with 0 electrical friction, 0 resistance, in other words. So you don't dissipate any energy as heat. All the energy you put into that electrical current goes where you wanted it to. Now, the price of that is, back in the day, you had to keep your metal chilled to a couple of Kelvin in order to keep it superconducting. These days, there are ceramic substances with much more interesting and difficult and complicated crystal lattice structures to them that you can, you only need to cool those to usually somewhere around 60 to 80 Kelvin to get them to go superconducting. So those are a much more accessible kind of superconductor. The reason why I said, Dad, but we still don't understand them, well, part of it is just, man, we're physicists, we're geeks, of course we want to understand everything, that's what we do. But the other part of it is, hey, if we could figure out why those ceramics go superconducting at such a high temperature compared to traditional metal superconductors, then, man, maybe there's a way we can boost that even farther. Maybe there's a way we can get up to room temperature superconductors. That would be awesome. That would change everything technologically. That would be a huge boost in energy efficiency at a time when we really need a huge boost in energy efficiency. However, since we don't understand, as well as we wish we did how high TC superconductors work, we also don't understand as well as we wish we did whether we can get that temperature limit even higher. However, today I want to go beyond that 70 degree Kelvin high TC superconductor limit. I want to even start thinking down to lower temperatures than that 1 or 2 degree Kelvin limit that were for the classical superfluids and superconductors. What are the coldest temperatures that humans can manage to achieve these days? Well, nowadays you will hear a lot of labs working in the nanokelvin region, which means they're measuring the temperature of the experiments they're doing on the scale of billionths of degree Kelvin. Now, how do you get something that cold? The way you used to cool things off to just 1, 2, 3 degrees Kelvin was pumping, evaporative cooling essentially. You would take your sample. Well, not always evaporative, but yeah, you take your sample, and if I want to liquefy nitrogen, for example, are we going to get liquid nitrogen here soon?
We can.
Yeah, let's do it. If we want to liquefy nitrogen,
I do have a video where we solidified nitrogen.
Yeah. The way you do that is you start pumping all where do you get nitrogen gas in the first place? Well, you're breathing it. The air is 80% nitrogen. So you start pumping all the air out of a chamber. As the air expands, it cools, just like if you take like one of those little CO2 capsules, CO2 capsule things that you use to inflate a bicycle tire or a soccer ball or something like that. As the CO2 rushes out of those things, you'll notice frost forms on the metal capsule that it leaves behind. Same thing's happening as the nitrogen gas rushes out of this chamber that you're pumping all the gas out of. The remaining gas cools. And if you do enough stages of this, pump it out, repeat the process, you can get that nitrogen down to, well, below 70 Kelvin is when it goes liquid. Continue that process, you can get down to about 1 degree Kelvin. But if you want to go for nanokelvins, you're not going to do it by pumping gas out of a chamber. The way that you hit the next stage of this, you start with something called laser cooling. Laser cooling is awesome. It was invented by a few people in the 1980s. One among them was Steve Chu, who was later the Energy Secretary earlier in the Obama administration. Steve Chu is awesome. Very nice guy. I knew him back in the day, but he probably doesn't remember who I am. But awesome guy. But how does the laser cooling work? Well, if I've got a collection of atoms that I want to cool down as cold as possible, I might be using, say, sodium atoms. Those are a good one for these Bose condensates we're going to be talking about. So I've got a gas of sodium atoms. How am I leaving them as a gas instead of a solid or a liquid? Well, that could be a whole previous stage on this, is managing to boil individual sodium atoms off of a crystal or a collection. So you actually start with a real high temperature process as you're freeing these sodium atoms to move around individually. Then you switch to a low temperature process. Is that?
Just saying, there's a lot of glare right there.
Oh.
Can you move it over and then
Yes.
make it a little bit bigger?
Yes, let's.
Thank you.
So here's my collection of sodium atoms. I boiled them using a high temperature oven off of a crystal of sodium of some kind. I've now got them suspended here at the crossroads of a pair of laser beams. There goes a laser beam. Here goes another one on another axis. In fact, since we live in 3 dimensions and not on a 2-dimensional whiteboard, I'll even spring for a third laser beam on the third axis going in like this. Now, laser beams are hot. Why the hell would they cool down these sodium atoms? Well, there's an awesome trick that you can do here. Remember, the inside of atoms function on the laws of quantum mechanics. They don't behave the way you would expect classical mechanics to do. And one thing that means is there's only certain energy states that they can be in. I'm thinking now of the electrons, the cloud of electrons that makes up the outer shell of each of these sodium atoms. They can be in the ground state. They can be in the first excited state. There's nowhere in between, though. So what you do is you make, and also for light, like the light waves that make up these lasers, well, this light wave has a wavelength. That means it has a frequency. Frequency would be the speed of light over the wavelength. And the fact that I'm using a laser instead of just a red flashlight or something means that every photon in this laser beam has exactly the same frequency. It also turns out the energy of a single photon of light, not the energy of the whole beam, but the energy of each photon, each particle of light in there, depends on the frequency. It's a fundamental constant of quantum mechanics called Planck's constant times the frequency. And what I do is I tune the frequency so that the energy of each photon is slightly too small to be absorbed by those sodium atoms. So I think of the sodium atom, I say this is a cold enough system already, they're all in their ground state. The electrons are all in the lowest energy state they can be in. And look, what's a higher energy state that I could shoot for? And I give these photons slightly too little energy. And the atoms have this heartbreaking, chance to say, man, I want to grab that photon and his excited electron up to the next energy state, but the photon's not quite enough energy. Maybe the next one will be. Well, no, the next one's not either. The next one's not either because it's a goddamn laser beam. The photons are all exactly the same energy. The poor atoms are, so close, yet they can never absorb any of those photons, except that these atoms are moving around. I kind of wish they weren't. I'm trying to cool them down to a lower temperature, but they are. And that means, suppose this photon's coming in from this direction, along one of the laser beams, and it encounters an atom that happens to be moving this direction, a little bit head-on toward it. Well, from the point of view of that atom, the photon is coming in faster. It's like if the train's going down a train track, if you're in a car on a parallel street and you're going the opposite direction of the train, when you look out the window, the train's passing you even faster than it would be if your car were standing still. It's a Doppler effect, essentially. This photon sees that reference frame shift. So they call this Doppler cooling, actually, because from the point of view of this photon, from the point of view of this sodium atom, that laser photon is going to be slightly higher frequency. When you're running head-on toward a source of waves, the waves reach you slightly more times per second, so you experience a slightly higher frequency.
So it experiences a higher frequency. It doesn't see the speed of the laser.
It doesn't see the speed of the laser change. That is absolutely true. You would think it would, but then Michelson and Morley, the people who started the experiment that led to Einstein's special relativity, thought it would too. It turns out, no, you do not see the speed of light change. Absolutely. And that's a whole nother topic for a whole nother day, but an awesome one. We might have actually done that one.
I think we have.
Sure. But you do see the frequency change. So if we were saying the frequency of these photons is slightly too small for the sodium atoms to absorb, hey, this sodium atom that's going head-on toward the laser can absorb that photon. So it absorbs the photon. The photons not only carry energy, but they carry momentum. Did you not know light carries momentum? Well, it does. Actually, even before we understood quantum mechanics, it turns out even in classical electromagnetism, light, electromagnetic waves do carry momentum. You can do something like a solar sail, where you put a big reflective piece of mylar up and you let sunlight bounce off of it. And they've actually talked about using this to very gradually accelerate spaceships because of the momentum that the incoming sunlight transfers to that mylar sail. Now, in this case, I've got this sodium atom moving head-on into the laser beam. It absorbs that laser photon, receives that kick of momentum, which slows it down. So this would preferentially slow down the fast-moving sodium atoms. A sodium atom that had been moving more slowly wouldn't have received that kick at all. A sodium atom which is moving the other way, and you'd say, oh shit, that one's in danger of being sped up if it absorbs a laser photon, but no danger at all because it's running away from those photons. So it's actually going to see them at lower frequency, and it'll have an even lower chance of being able to absorb that photon. So this is saying, all right, the sodium atoms will preferentially absorb photons that they're hitting head on, and that collision will slow them down. Using this, you can slow this gas of sodium atoms down to about 1/1000th of a degree Kelvin. We're still not down to a nanokelvin, but we're getting closer here. So now we're down to the millikelvin range. Why can you not slow it down even further? Well, because after absorbing that photon, the sodium atom's now got to give it up. And so if I've got a sodium atom, which is now in an excited state, so I'm kind of drawing with a more wiggly than usual electron wave function, which is a terribly unartistic way to draw this. But this sodium atom, a little star on it, can mean that it's got some extra energy. But it's got to give that energy up, and man, maybe I managed to bring it to an almost complete halt, but then when it gives the energy up, it'll spit a photon out in a random direction, and it'll recoil, because again, it's spitting out a photon that once again has momentum. So if it spits out a photon that way, the atom will recoil back this way. Now at first this doesn't matter, because at first the amount of recoil you get from a single photon just isn't enough to really make a difference. But by the time you get them really slowed down, it hits the point where the limit of how cold you can get them is that you know that when they give up the photon in a random direction, that they'll recoil with at least that much momentum. And that's kind of the coldest temperature. They call that the Doppler limit of how cold you can get these things. And it's typically about 1,000th of a Kelvin. So at that point, you're SOL when it comes to laser cooling. Still, Steve Chu is awesome, but the process can't take you all the way. So what do they do next? Evaporative cooling. Well, that sounds like what you do when you set up a swamp cooler in a tent or something like that. However, what you do here is you've now got this much colder gas of sodium atoms. You turn off the laser beams; they won't do you any good anymore. But how are you confining this gas in the first place? How are you keeping it from just kind of falling to the ground of the chamber? I mean, it's not like it's immune to gravity. Well, you got it confined with magnetic fields. So you've got your distribution of gas atoms, and you've got what they call a magnetic bottle sometimes. You could almost, if I'm drawing the potential energy landscape, you could almost say it's like a hole that you can store the atoms in. It's not physically a hole in the ground. What I'm drawing is that you've got less electromagnetic potential energy if you're in this area. But your atoms are at various levels from very low energy through almost enough energy to escape from this magnetic bottle that you've put them in, and kind of anything in between. And the average energy of them is telling you how cold they are. Well, at this point you're saying, I want this thing even colder, so I want to get rid of the highest energy atoms and just keep the low energy ones. So I'm sacrificing the number of atoms I have in this gas in return for getting a much colder average kinetic energy. So I momentarily turn down the intensity of that magnetic field. I think at this point you radiate that sodium gas to give the atoms little kicks from photons they absorb. But you shake it up a little bit, you lower the walls of that chamber, and just like for the same reason that when water evaporates, the reason why you feel colder, if you're outside on a cold day and your skin is wet, it suddenly feels a lot colder. And the reason is, you've got this layer of water on your skin, the water molecules are each moving around with a different amount of energy, but the ones that are most likely to escape into water vapor, the ones that are most likely to evaporate off your skin, are going to be the highest energy ones, which means that the average energy of the ones that are left goes down, and the water gets even colder as it evaporates. Same thing happens here. As you evaporate off the high energy sodium atoms, the ones that remain behind now have a lower average energy. And you repeat this process over and over again. You turn the magnetic field back up. You let the atoms re-randomize and redistribute their energy. You turn it back down again. You hit it with a little radiation kick again if that's what you're doing to shake them up somewhat. And after enough cycles of this, you actually can get this cloud of sodium gas down not to 1 nanokelvin. When I said in the nanokelvin range, well, I think a state-of-the-art experiment these days would be in 100 nanokelvins. So you're measuring it in nanokelvins. You're not down to a single nanokelvin. Or maybe it's even better these days. Maybe I'm behind the times when I say that. But yeah, this is pretty damn cold. Now what happens at these temperatures? I said at much higher temperatures, just a few degrees Kelvin, you could get helium to go superfluid, you could get ordinary metals, not high TC ceramics, to go superconducting. What can you do at the nanokelvin range? Well, this is when you start creating a state of matter known as a Bose condensate. Now, what's a Bose condensate? Einstein Bose condensate is the full name. It's named after Albert Einstein, who you've probably heard of, and the Indian physicist Bose. They conspired to work out the properties of this state of matter way back in the 1920s, well before it was possible to actually realize this stuff technologically. But what's going on is the fundamental, I mean, again, this state of matter would not exist without quantum mechanics. So you need to know something about the way quantum mechanics works to have any understanding of this. What's the most important thing to know about quantum mechanics? All the fundamental particles of nature, first they have spin. Now you might say, well, so do macroscopic things. Look, this is spinning around right here. Well, then the planet we're on is spinning. The weird thing about quantum spin, though, the thing that makes quantum spin to me actually even weirder than wave-particle duality is a quantum particle spin. For example, an electron, which has a spin of 1/2 h bar. H bar is a constant closely related to this Planck's constant here, h. 1/2 of that, well, the units of h turn out to be angular momentum, so 1/2 of that's just telling you how much angular momentum the electron has. It's got a spin of 1/2 h bar. Now you might say, great, what axis is it spinning around? Take your pick. If you measure the spin of an electron around the z-axis, you will either get plus 1/2 h bar or minus 1/2 h bar. Not on the average, those are the only two values you will get. It's either spinning with this exact amount of angular momentum this way, or it's spinning with that exact amount of angular momentum that way. It's never not spinning, it's never spinning slower, it's never spinning faster. You can't speed up the spin, you can't slow down the spin, you can only flip it between those two values. And then you say, well, what if I measure it around the x-axis? Same thing, around the x-axis, it's also either spinning that way or this way. You say, wait a minute, I'm the one, I just made up the x and z axes. It's not like nature knows that would happen. What if I spun it around an axis that's almost the z-axis but 10 degrees off? Well, around that axis, it's either spinning this way or that way, with that exact plus or minus 1/2 h bar. It's almost like nature is trolling us or something like that. It's quantum spin is a really weird thing. To further amplify the weirdness of it, if you've got particles that are half-integer spins, like that electron whose spin was 1/2 h bar, if you have two identical particles, two electrons that, all electrons are identical to one another, they have exactly the same properties. But in quantum mechanics, identical doesn't just mean, you can't tell the difference by their properties. It means nature does not actually consider these to be two different particles. If I've got electron number 1 that I'm going to name Fred, and electron number 2 that I'm going to name Diane, and Fred's over here spinning this way in such and such a momentum state, Diane's over here spinning some different way in some, trapped in some region with a harmonic oscillator potential. And then I said, what would happen if I have them trade places? If I said, let me think about a state of nature where now Fred's over here and Diane's over there, and they're each doing exactly what the other one was doing. Hey, well, since I switched them, that's a whole new state of, a whole new state that this quantum system can be in, right? Well, it's not. All nature cares about is that there's one electron over here doing such and such, another electron over here doing such and such. It doesn't know, it says there's no difference between those electrons. You switch them around, you've still got the same state. Now, you follow up the mathematics of this a little bit more, and what you find is this leads to two possible consequences. Either no two particles can ever both be in the same state, or particles will love to both be in the same state. And it turns out that spin 1/2 particles, what we call fermions, absolutely refuse to be in the same state. So no two identical fermions, so no two electrons, no two protons, no two muons, identical particles can be in the same quantum state, can both be doing the same thing. This is the basis of all of chemistry. This is called the Powell exclusion principle. And this is why if I go to the periodic table and I say, oh yeah, there's an atom called chlorine that has 17 electrons. Well, you'd think, okay, well, you've got 17 electrons, but there's a lowest energy state they can be in. Cool, let me just put all 17 electrons in that lowest energy state. Nature always likes to put systems in the lowest energy state you can find. So if chlorine's got 17 electrons, that's where they should all be. And then I find that I can't. Because, again, I can only have one electron per quantum state in there. If you've ever taken a chemistry class where you say, oh yeah, the electron configuration of sodium, 1s2, 2s2, 2p6, blah, blah, blah. What you're doing is you're listing off all these various quantum states, and you're saying, I can only put one electron in each one, so that 2p6, for example, means in a certain subshell called the 2p subshell, there's 6 different states available. I filled them all. So all of those are full of electrons. I got to move on to the next subshell for the next electrons and so on. Without the Pauli exclusion principle, there would be no such thing as chemistry. Every element would just be a souped up form of hydrogen. No two elements would really behave different from each other in any interesting way. And essentially, all of the fascinating structure that we get from the fact that there are different chemical elements that each have their own unique chemical properties, none of that would be true. The universe would be a very boring place. So while I still think quantum spin is the weirdest freaking thing there is, I'm kind of glad that it's out there. I mean, none of us would be here without it.
Go spin.
Go spin.
Can we
yes.
wrap it up in 5?
Okay. Bosons are the opposite. Bosons are things whose spin is an integer. The photon, the particle of light, is a good example of a boson.
Hello from England and Mexico.
Hello
Right.
from England and from Mexico. Welcome aboard. Sorry that we're almost to the end of this, but bosons are integer spin particles. You've heard of a laser. If I said that the reason chemistry works is because fermions hate to both be in the same quantum state, the reason a laser works is because bosons love to both be in the same quantum state. When you excite a laser in that resonant cavity between two mirrors inside the laser, the trick is if I can get one photon to start resonating back and forth in that cavity, it becomes twice as likely that a second photon will want to enter that same state. Come on in, the water's fine. Once I've got those 2 photons there, it becomes 3 times as likely that a third one will want to enter, and so on, to the point where, as I get more and more photons resonating in that cavity, the chance that I can send in another one gets greater and greater. If this was a talk about lasers, I would go on and explain to you the importance of population inversion and things like that and getting this laser to work. But the whole, if I'm thinking about the properties of fermions and bosons, the whole reason lasers work is because bosons love to have more than one identical particle in the same state. Now, that's great. A photon, a particle of light, is one example of a boson. What's another example? Well, these sodium atoms, their nucleus contains 11 protons and usually 12 neutrons. This is sodium-23 is the isotope I'm using, so definitely 11 protons and 12 neutrons. They've also got 11 electrons around them, and at a cold enough temperature, all of those particles can kind of combine their spin and act as a single composite particle. If you've studied any quantum mechanics, you have to get down below the hyperfine splitting energy before you can combine the spins and they won't kind of randomize. But this is what you're doing as you enter these nanokelvin temperatures. So you're getting cold enough that a sodium atom made out of 34 different particles, 11 protons, 12 neutrons, and 11 electrons, are kind of acting like one giant particle with an integer amount of spin. So that means now each sodium atom wants to be doing exactly the same thing quantum mechanically as all the other ones around it. They want to all enter the same quantum state. We said this is kind of like what photons do under normal circumstances. What can you do with photons? Well, you can make a laser. One thing that they can do with these Bose condensates is they make something called a matter laser. And in the same way that with a photon you can send a beam of coherent light particles out across space, with a matter laser you're sending a beam of coherent matter particles, a beam of sodium atoms in this case, that all have exactly the same momentum, they're going in exactly the same direction, they are in phase with each other quantum mechanically, which means you can do things like set up interference patterns on that distant screen. This is an awesome thing for fields like quantum computing. You can now be manipulating the behavior of individual atoms on a quantum level, the same way we've always been able to manipulate the behavior of individual photons. And for example, I was just reading something earlier today because I was kind of trying to learn what's been going on in this field for this talk, to where you can take a laser, encode a quantum information bit. This is the quantum computing version of a bit of information, except that in quantum computing you can have your computer essentially almost working in parallel with itself. The bit doesn't have to just be on or off. It can be in a superposition of the on state and the off state. And each of those possibilities can kind of be continuing through the processing cycle independently of the other. So you take this weird superimposed on-off qubit thing, encoded in a laser beam, which we've always been able to use to hold qubits. And they say, now you can send that laser beam through a Bose condensate, get the Bose condensate to absorb that information. There's no loss from noise because all the particles in that Bose condensate are in sync with each other, all doing the same thing. You turn off the laser. You'd say that qubit's gone now. I don't have that laser pulse anymore that was holding it. You turn the laser back on, let it interact with the Bose condensate again, and it can pick up that qubit from the Bose condensate and continue on as if nothing had happened. Now, do we use this to build powerful quantum computers? Well, no, not at the moment we don't. We're just kind of figuring out that this kind of thing can be done. But if you're interested in quantum computing, if you're interested in nanotechnology in general, then you'd say, yeah, this is the pioneering work to say we're starting to be able to manipulate the quantum state of individual atoms. And that's something humanity has never been able to do before. Which is awesome, except we never got to the thing about temperatures lower than absolute zero.
No. We'll have to do that next week.
In the future, we will.
Yes.
This was actually cooler. The temperature's lower than absolute zero is kind of a technicality thing. It is cool, but it's not quite as cool as laser cooling and Bose condensates and all that kind of thing. But we haven't forgotten. We'll get back to that. I know, though, Joe's got demands on his time. We got to run.
We can pick that up next week. Paul, thank you. All right, so that was Paul Graham. Paul, thank you so much. We will be here next Wednesday, 3 o'clock Pacific Standard Time, and talk a little bit about temperatures below absolute zero and that.
Yes.
Okay, we will definitely cover that, and you've got lots of thanks from people all over the world. Thank you for tuning in, and see you next Wednesday.